Good. So let's make a start. This afternoon, I don't know if it's possible for us to put in two subtopics during the afternoon. I'll try to see. So first, we'll deal with the topic of work, energy, and power. So we'll start with this, right? First of all, we want to clarify what we mean by all of these terms because they're used a little differently in physics. Like some of you would say, today I went to work, and all you did was, maybe you're no offense to anybody who does office work, right? And you sit in your office and maybe you do some work on the computer, and so that's not the work we're talking about, right? Um, for me, when I do any kind of deep thinking for my job and research, and so I said, man, I work all day today. I worked on this research idea, or um, that sort of thing. So, but that's not the way work is defined in physics, right? um, it's a little different, right? Even energy. Um, like sometimes you hear your children. Maybe I know some of you are parents in the class. You have some children and they're hi, yeah, yes, I'm in a class, right? Yeah, yeah. So um, and a child is misbehaving and whatnot, and you're fretting over the child, and yes, I'm in a class. You all got to go in front. Yes, I'm in a class. Yes. My grandchildren, man, they come this afternoon, and well, I have to be in this class. Yeah. Sometimes the children, they're misbehaving, and you're fretting over them, and so on. Some people say, don't waste your energy behind them. And lots of times that means mental energy, right? It's not what we're going to be talking about, right? Energy in physics might very well be, not might, it is defined differently. Power too might be defined differently, right? So we're going to get into what they really mean, right? And the little notes that I sent to you, um, some of you might have seen it, maybe did a bit of reading. I'm sorry that only this morning I sent these notes to you. But this is a little definition of what work really involves in physics, right? Give me a second to just. Yeah, good. So this is a little definition of what we mean by work in the context of physics, right? Basically, when a force acts on an object and it moves through some distance, we say that work is done, right? So listen to that definition carefully. When a force acts on an object and it moves that object a certain distance, we say that work is done by that force. And that's what you're seeing in this little equation here. Let me demystify the equation, right? So this W means work, right? We're quantifying work here, right? How do we calculate then? How do we quantify how much work is done? So work is a quantity in physics, and it's defined by the force that is exerted on an object multiplied by the distance that the object moves. So this F is the force, and this S is what we call this displacement, right? Distance in a specified direction. Well, we can, instead of saying all of that, you say the displacement, right? And the force and the distance, well, they're both in the same direction. Good. So why this cos theta here? Why this cos theta? Because at times you have a situation, and I think there is one in the notes where somebody is pulling a suitcase. So the force is pulled this way, right? So maybe this is the suitcase, you get a suitcase here, right? And the wheels are there. And it's being pulled along this way. So the distance moved will be S. But here, the force is not in the direction of it's not in the direction that the suitcase is traveling, right? There's some angle here. So what happens is when we resolve this force downwards, because the force has to be in the same direction as the distance or the displacement, right? So when we resolve this force, it's going to be F cos theta. So this is the force acting in this direction, F cos theta. And that's why we are saying here that the work done is F cos theta by S, right? If you are pulling something, let's say on a flat surface, maybe all right, the thing has wheels, and you are pulling it along like that. Maybe the thing is pretty large, and you are here, and you're pulling at this thing here, and you're pulling with a certain force F, and the thing moves, it moves from here to here, right? And you pull it along here, S. Then work done is simply F by S. If you don't like S and maybe D is used, we can use FD. Some textbooks use FD, right? Here you don't have to put cos theta because there's no angle really. You are pulling this, let's say it's a little trolley or something, and the trolley you're pulling it in the same direction in which it's moving. So there's no cos theta involved. There's no resolution of forces taking place. Here you have to resolve this force, and the force that is horizontal is really F cos theta. Now the force is in the same direction as the displacement. But in this case, there's no resolution needed. The force is actually parallel to the distance you are traveling or the displacement that you are moving the object, right? So that's the difference there. And that's how work is defined in physics, right? Work done by a force, really. It's the product of the force by the displacement that it moves the object, right? That's how work is defined in physics. So we're not talking about mental work here, right? So yeah, you could be a watchman, and you say, I'm working tonight. And all you do is maybe you sit down and you watch the premises of a place, right? In physics, no, that's not work, right? So keep that little difference in mind, right? Keep this difference in mind. As you can see here, the unit for work, remember, it's force by distance, and they come up with a unit called the joule. So it's equivalent to 1 joule. 1 joule is equivalent to 1 Newton times 1 meter, right? But we don't use Newton meter as the unit. Well, the reason why is that there's a famous scientist by the name of Joule, right? That was his name. And as a tribute to him, right? As a tribute to him, they said, man, look, And my computer is misbehaving. I wonder why. 1 second. I wonder why my granddaughter is crying so hard in front there. Yeah, okay. And something was she must be misbehaving and they put some lashes on her. Yeah. Yeah, so the name the unit Joule, right? There was a famous scientist, I think his first name was James or something, James, something Joule, right? Joule, sorry, Joule, not um the plural, right? Well, I'm saying is the man's name can be a plural, yeah. His name was James Joule, right? He was, I think he's from England or somewhere here. So because he did a lot of work, right? Did a lot of work when it comes to, work and energy, and so they named or they said, look, let's use his name as the unit for work, right? So 1 joule is basically if 1 Newton is exerted on a body and it moves 1 meter, well then that's 1 joule. I use that as the unit, right? Um, Good. So let's move on now. So let's talk about energy, right? And energy again, it's defined a little differently. It's defined a little differently um, from the way we, sometimes use the word energy, right? In everyday conversation, right? And energy basically, you see this definition that energy is the ability to do work, to do work, right? And what basically this is saying is that for us to accomplish work, to do any work, energy has to be expended, right? So that's why you say that, well, okay, energy is equal to work done, right? Work done, right? So if you want to say energy expended equal work done. Yes, there might be again when we talk about work done here, um, we might very well be talking about a mechanical work done, right? Sometimes you expend a little more because oftentimes you have losses and you might expend more energy and you lose. Like, okay, we just talked about you pulling a suitcase, maybe, right? You're pulling a suitcase along, okay, the suitcase is here, has a wheel, and you're pulling it along with a force, right? And you might find that you exert a little more than if you were to calculate the work done. The suitcase moves from here to here. But what we didn't consider is that maybe the suitcase, the wheel has some friction, and you have to expend the energy to overcome that friction, right? So don't always say that, well, okay, it's the distance traveled, right, by the force, and we said this time we will use F cos theta if this is the angle here, right? Um, Sometimes you might have to expend a little more than that. So they make it's the mechanical work done, and then you also have other things come into play, right? Work done um, in moving the object, right? Plus overcoming resistive resistive forces, right? So, and we're not going to get into these complex situations, we're going to, deal with a very simple situation, right? And that is why sometimes in the questions you will see that they will tell you, man, you know what? Neglect the resistive forces or the frictional forces, right? And you will just neglect those in your calculation, right? Yeah. So this topic here of energy. We say energy is the ability to do work, right? And when you calculate the work done, well, you need energy to do it, right? And that's the relationship, the work energy connection, you know, the work energy connection. And there's some nice examples in the notes. You'll see one, I think, with a suitcase. Example one, pulling a suitcase on wheels, right? Maybe let me just chop it quickly and bring it into the notes. Sorry, bring it into the thing here. If you went through the notes, you will see this here. Control V, what's happening here? What's happening? Sometimes the thing is bringing back some other control. Oh yeah, now finally. I I guess you remember seeing this in the notes that I sent to you. Very
Yes, sir.
simple situation. A woman pulling um, a suitcase along at the airport, perhaps, right? And usually, and again, one of the things I want to mention here is that man has um, they have developed all kinds of mechanism to make work easier because energy, having energy to do everything, right? And it's I would say energy is in a limited supply, right? Whether be it physical energy from human beings, whether you have to extract energy from um, you know, whether be it oil or coal or nuclear energy, and so it's always a problem of economics and so, and therefore, we have to resort to creating machines to make things easier because if you have to lift your suitcase, right? If you have to lift your suitcase, think about this, right? Think about this. This suitcase is all right. They didn't give us the mass of the suitcase. They give you um, okay. They just give the pulling force here. They didn't give you the mass of the suitcase. I wonder. Uh, what's the average weight of a suitcase? Maybe about 20 kilograms. Think about it. Let's see. Let's see. If you have a suitcase about 20 kilograms, and if you have to lift this suitcase and move it, let's say 100 meters, right? 20 kilograms. Um, this would be what? 20 G, or we put it 200 newtons. So the work done would be equal to, my space is limited here, would be equal to 200 newtons by 100 meters. And you would have to expend 200 by 100 is how much? 20,000 joules, right? Or 20 kilojoules. That's a lot of, that's a lot of energy, right? That's a lot of energy to expend to lift that suitcase. On the other hand, look at this problem here. This person is pulling this suitcase with 45 newtons, And okay, the force is making an angle of 50 degrees, and they're pulling it 75 meters. All right, I should have gone with 75 meters here, right? Okay, now this 45 newtons, what does this force really, what is it overcoming really? Is it lifting the suitcase? What is it doing? Do we need to lift the suitcase in this scenario here?
No, sir, we need to pull the suitcase.
So we're doing work against what really? What force are we doing work against? Is it the weight of the suitcase? Are we lifting the suitcase?
No, sir.
No,
We're
what
pulling
we
it. We're
actually
pulling the weight
doing,
of the
we are
suitcase.
just overcoming the frictional force between the suitcase and the ground. Don't get me wrong, weight plays a role because let's say the frictional force, let me just tell you this bit. It's not in our course, but frictional force, right? I'm sorry, I'm using F again. Um, frictional force. It's equal to mu times R, where mu is what we call the coefficient of friction, and R is really what we call the normal force. And R in this case will be equal to the weight of the suitcase, mg. Right? Frictional force, let's say because of the suitcase, many of you see suitcase wheels, right? Very often, they roll easily, they spin easily, right? And the friction between the ground and the wheel is always very small. So mu might possibly be like, let me say, all right, 0.1 or 0.2, right? It's a very small, well, depending on the kind of wheels you have, right? Rubber wheels may have a little more, and they have these shiny plastic wheels, right? They're noisier, right? They're noisier, but the frictional force might be very small. So if let's say the suitcase was 20 kilograms, then the frictional force you have to overcome now, notice, it's not the 200 newtons, it will be 0.2 of that 200 newtons, right? So because you are rolling this thing on the ground, you only have to overcome the frictional force. It's not that you have to exert 200 newtons because you're not lifting the suitcase bodily and fetching it 100 meters. You are simply pulling it along. So let's say, all right, the wheel makes it has a coefficient of friction of 0.2. Then the frictional force that you have to pull with, right, will be 0.2 by 200, which is far less, than this here, right? Far less. Of course, I'm deviating from this problem here, right? So the frictional force you have to overcome is so little. It's so little, right? I think I confuse you with this. This problem is a different one, obviously. You will read about it, but I'm just explaining to you the difference, right? And that's why we make all these machines, right? And these contraptments so that we don't have to do as we say, use brute force and ignorance. If you have to fetch a suitcase, right? And some of you, when you're going outside, you got to carry pepper sauce and you got to carry fish and you got to carry all kinds of things for your family. And you load up the suitcase, 50 full pounds. And people wait and then say you can't carry all this and take out some of your thing and thief it and so on. All kind of things that's happened. So yeah, and sometimes you gotta call like your relative, come, take back this carrot home. You know, all kinds of things happen at the airport. So, but the point is, we don't have to do that anymore. They devise the suitcase in a way that you can roll it along. And what you do, because you only now have to overcome the frictional force, right? The force you exert is far less now, right? It's far less. So you only have to exert, what's this? 0.2 of 200 is how much? Somebody
40,
multiply.
sir.
40. Look at this compared to this 200 newtons here. Look at this. If you have to lift the suitcase, right, you'd have to exert that. But now, because the way they designed the suitcase, you only have to exert 40 newtons now to pull it along, right? So this F cos theta must be equal to 40 newtons to pull the suitcase along. And you're okay, right? And you're okay. I know my working here has to do with a different type of problem. You will read this. Anybody had difficulty understanding this problem, though? The one that is on the in the notes?
Sir, I'm now getting a chance to go through it.
Okay.
The notes.
Yeah. Well, this one is just an application of the formula, right? The person is pulling with F. The angle that their body and their hands and so make with the ground is 50 degrees, right? And they're pulling it 75 meters. And that's the work done. It's just a formula. But what I was showing you just now is okay. If I'm to give you a scenario, so let's go back. I'll go back that one. So you have a suitcase, has a wheel here, and you're pulling it along, right? Your hands they're on here. You're pulling it along, right? And you're walking away. Good. All right, let's go with that. Let's say it makes a 60 degree or something, right? The weight of this suitcase is, okay, let's say it's all right. The 200 newtons we had just, right? It's a 20 kg suitcase, so the weight of it will be 200, right? The reaction to the ground, right? Well, this is going to press down through. It's going to press down through the wheel, and the ground is going to react. The ground is going to react with 200 newtons, right? Let's use mu, which is the coefficient of friction, as we said. Let me go with 0.2, right? So if you're asked what force you need, what force here you need to pull this suitcase along, right? What force you need. So look here. If you are to resolve this force this way, F cos 60 is the force you need, right? So acting this way is the frictional force, mu r. So F cos 60 degrees is equals to mu, which is 0.2, times r, which is 200 newtons, right? So F then would be equal to 0.2 by 200 newtons over cos of 60 degrees. And can somebody tell me that? Anybody has a scientific calculator with them?
Sir, it's 80.
80 newtons. All right.
Yes, sir.
80 newtons, right? So here, this force is going to be, you notice that this force is a little larger than this force. You see that? F is 80, right? While FR, let me show you what I'm talking about. F cos 60 is going to be 80 cos of 60 degrees, which is going to be what? Give me 80 cos 60.
Sir, 40.
40.
40
Sir,
degrees.
40.
Good. Now answer me this question. If this force here is 40 newtons, and this force here is 80 newtons, why are we pulling in this thing with 80 newtons when we can do it with 40? Why? You only need 40 newtons. Why are we exerting 80 newtons? Why?
Sir, the angle?
What about the angle?
The smaller the angle, the more force you would need to pull it. I
No,
think.
forget the mathematics. Think about the human aspect. If you had to pull your suitcase with your hands down like this, how comfortable will it be?
Not comfortable.
It's going to be very uncomfortable, right? It's going to, because you can't get your hand down so low. It's going to be uncomfortable for you because you have to bend over. So while it might pull easier in that it's less force to pull it, it's uncomfortable because of our build or human body, right? And that's why we pull it at an angle like this. You get what I'm saying? So the physics is saying, man, pull the thing parallel to the ground. It's less force. But when you think of the human body, you know, lots of times, and you will see this, and you mustn't forget that human factor as you study everything. It's easier to pull it like that. In terms of, not easier, I should say, let me use the right words. You need less force if you were to pull the suitcase parallel to the ground, right? If you were to pull the suitcase and the force is exerted this way, you need 40 newtons. But here, because of you pulling it like this, you need double 80 newton. But this is better because of how we are built, right? How we are built, the practicality of it. Look at the girl that was inside. If I'm to go back to this picture here, right? She's pulling it comfortably along. So she's using a larger force. Of course, it's better than lifting the suitcase bodily. It's better than that, right? If she was pulling it along the, or pull it parallel to the floor, she would need less force, but she'd have to bend her back, right? And that's what this course is about, you know, that extra, that human factor, that human element that we're talking about, right? You want to think now of, okay, human beings, and when you're doing certain things, right? Granted, let's say the boys who maybe they work in a warehouse, maybe even some of you girls probably in a warehouse, and yes, if you were to pull something along, you know, parallel to the floor, it might require a smaller force, but you realize when you bend over your back like that, it hurts the back. It is very uncomfortable for the human being to stoop down and pull something along parallel to the ground. And that's why the suitcase has this mechanism. And you will see the trolleys that you use. I have a warehouse at the head of my street here, Ansel McCall, and all their trolleys, you'd see them. These boys would pack enormous amount of weight, but the trolleys all have an like a flexible handle, just like this girl here. She can angle the handle as she see fit, right? Some of you probably, when you I don't know if any one of you, my wife had one, and the other day it broke. One of these things we fetch gas with. So we have something, and it has a wheel here, and there's a little contraption like this, and we put the gas bottle here, you know. Anybody got that at home? And the gas bottle rests there. And we normally, okay, it's kind of you know, something like that. Yeah. And we put a gas bottle here, right? And we pull it along. We pull it along. I think we angle, the thing is short, right? So we pull it like that. Forget this here. Anybody has that at home? Where the shop is
Yes,
nearby,
sir.
and instead of fetching the gas, you roll the thing along and you put the gas in it, and you know. So yes, this is a nice everyday application of the thing. So while if I were to angle this thing and pull it this way, you might need less force. I wouldn't stoop down and bend over and roll. Everybody say, what's wrong with this man? You understand? It's not practical. And as I told you, the warehouse in front here, these boys would pack an enormous amount of these cases, you know, on the trolley, and they'd pull it very comfortably. And those trolleys, they'd have these rubberized wheel, and they have a double wheel. 4 double wheels. And they put, I think it's about a ton of stuff they put on it, man. And they'll pull it along very easily, right? Some of the wheels, as I said, depend on the type of wheel, like your rubber wheels. Some of them, those might give you a little more friction, right? While they have these wheels that will be more like plastic. They have less friction, but guess what? They're very noisy, right? And they break easily and those are all practical things you got to think about. People say, well, why do we have rubber wheels if they have more friction? Rubber wheels are more durable, right? So while rubber wheels give you more friction, you have to exert a little bit more force. The plastic type of wheel, less friction, but they will break easily because plastic is not as strong and what is a resilient like rubber. Rubber distorts and come back to its shape. Plastic, you put some weight there, it's brittle. The structure is not resilient, right? It absorbs the energy and cracks. So the impact and so on cracks, you know? So those are the kinds of things you have to consider, you know, not just the mathematics or the physics. You want to think of the practicality, right, of certain things. Good. I think there's another example there. All right, maybe let's do this one. I'll cut this one out and bring it over as well. I'll give me 1 second. Let me put on this light. Yeah, it's getting dark now. A little early. It's not even 6 yet, and it's almost getting dark. And there was this problem here. Get the weight, the person lifting weight. Oh, not this one. I don't know why the same thing is coming up over and over. All right, good. I hope this. You saw this one, right?
Yes, sir.
So here is somebody doing some bench presses. And I guess you guys, there are some of you who go to the gym here. Maybe after all the work you do, you still have some energy to go to the gym. I have a gym on the road here. I forgot. I think the gym name is Lift. Lift. I think people don't go to that gym for no exercise, right? When I pass by that gym, first of all, they create a terrible traffic congestion. Everybody comes to the gym with their fancy vehicle. You know, when you pass, now there's nowhere for you to pass. It slows up the traffic, right? And then you see all of them go there and the way they're dressed and what I think it's all about fashion and boys coming to check out girls and girls coming to check out boys and you know just a social place. I don't see it as I don't think they come there to do much exercising. I was asking somebody if they have you know showers and so at the gym. This is one country. The gym should have a shower. So when you finish bathing, when you finish exercise, you want to bathe. And you know you can be able to go back in your vehicle and you will have a fancy vehicle and you come out all sweaty. Let's say you decide to team up together, 4 or 5 of you jump in a vehicle and all of you are smelling. Oh my, no amount of perfume can get rid of the scent. you know, the port. My look. Yeah. All right, let's stick with the physics here. So some weightlifting, right? So this guy is lifting a weight of 710 newtons, right? He's bench pressing. That's the word they're using there, right? And we're going to assume that he, is the movement of the weights is vertical, right? So he has to lift the weight 0.65 meters above his chest, and then he has to, okay, when he lifts the weight, so he has to exert energy to lift the weight to that position, right? And when the weight is coming down back, remember the weight, oh, by the way, we're coming just now. We're coming just now to something called gravitational potential energy. And you will understand that what we're talking about here a little more, right? So when he's lifting the weight, he has to work against gravity, right? He has to lift this weight up. And the gravity is pulling the thing down. So he has to work against gravity. And the work done is, okay, that same 710 newtons. Well, cost zero is 1. Forget this cost business, right? As I said, if the force and the distance is in the same direction, there's no need for the cost, right? So there's no angle involved here. He's pushing the force straight up, and the weight is moving straight up as well. So there's no angle. And that's why cost zero is 1, right? If you know a little bit of trigonometry. Take all the cost business out of it. So the work done is that 710 by 0.65 meters, which is 460 joules. So he has to exert, right? The work done against gravity, there's 460 joules, right? And as I said, when you think of the work, energy connection, he has to exert 460 joules to do one bench press, right? To push it up there. He's not done yet, because when the weight is up there, he can't drop it down and fall on his chest, he dies, right? He could break a couple of ribs. And again, this is a nice practical example. I think this is a bad idea, right? If you go to the gym and you're doing bench press, what should you do? You're doing this kind of thing, what should you do?
Have a spotter.
Have a
A spotter.
or that's what you call it, a spotter?
Yeah, someone to be there with you.
Oh, okay. I never heard that term in connection with this. Okay, all right. When I was a kid, I used to lift weights in. Yeah. Yeah. We made weights out of lead from batteries, and we had 2 flywheel as well from an old vehicle. Yeah. All right. So you have a partner. You have somebody said spotter. I never knew that's the term. Thank you for educating me. Right? And that person is always there, because if you take that weight up there, right? Sometimes you struggle and then the weight is up there and you can't bring it down back. What happens? You understand? You drop that weight on your chest, you get some broken ribs, possibly you crush your lungs and whatever else, So yeah. So you need somebody to be there, right? However, all right, the person is there, but you said, no, I can lower this weight. Now you remember, gravity wants to pull that weight down, right? And you now have to work against, you got to actually now work against gravity now to lower that weight slowly, right? So remember, we treated in this problem up as positive, down as negative, right? So in this case, the force is 710 newtons. Notice they're using cos of 180 degrees because they're saying coming down is a whole 180 degrees, like a about turning, right? As I said, you can neglect this and you can treat the 0.65 meters as a negative distance. You can treat that distance negatively. Or you can treat you can treat the force as negative, meaning it's coming down, right? It's up to you. The result is that you actually exerted another 460 joules, right? So in all, you have actually exerted, how much is that? 460 plus 460, right? You have to add that amount of energy to do one bench press, up and then down. That's a lot of joules, a lot of calories you'd have to burn, right? When it comes to, doing a bench press. Right, and I wonder something is going on with my computer with this particular. Let me see if I can get rid of this. Yeah. Um, yeah. So if you're a person who if you are a person who does some exercising, anybody goes to the gym here? Maybe with the bad things I said about the gym just now you'll be ashamed to or shy to tell me you go to the gym. Anybody get a time for a workout? Hmm? Nobody? Yeah, I just mentioned just now about calorie, right? Um, Again, it is an old unit that refuses to go away, right? It's not the SI unit for energy, but lots of times you have that um, you see the use of the word calorie. Let me just mention this here, right? And one calorie is approximately, they have 4.1, what is it? 184, but forget this here. 1 calorie is about 4 joules. 1 calorie is about 4 joules. Or that 0.184. We're not doing rocket science here. So when you read, let's say you're reading the labels of foods, right? And you want to know how much calories, right? Sorry. You see the thing is in calories. Anybody when you read the labels on things, right? Let's say you're eating a candy bar, right? A candy bar. And the candy bar says that this bar has 400 calories. Calories. You want to know, well, what does this mean in terms of energy, in terms of joules? Well, that would mean that this thing has 100 joules, or it could give you 100 joules of energy, right? That's what they mean. And usually they'll tell you that one serving, right? I don't know. Let me see if there's a standard. Let me see. One serving. How much is that? One serving. I'm asking the internet. How much is one serving? Let me see what they mean. If there's some standard. Not seeing. I don't see a standard. There don't seem to be a standard of what they're calling one serving. I'm trying to see American Hearts. So 1 second. I'm just trying to see what they mean by what is a serving. So they're saying for grain, I'm not seeing how they're saying how much is a serving. That's something if you can research and share with me on, it would be nice. I'm not seeing a standard definition saying okay. I'm not seeing how much is a serving. So when that's the thing, when they tell you that, well, all right, 400 calories per serving. I don't know what they mean. Do you? Do you know anybody? When you read the label, so you pick up an energy bar at a supermarket, and it says this energy bar has 400 calories per serving. What what do you make of it? You have to know how much is a serving. Is that bar
Or
one serving? Uh-huh.
sometimes on chips they would say like 10 pieces of chips is a serving, or like on a chocolate bar it would say like two squares or something like that. Some packages say that, but some packages would leave you wondering if
Yes,
it's
yeah,
the
that's what
whole
I'm
thing.
saying. Yeah. If the food industry is something else, eh? Yeah, I know I'm getting out of physics here, but it's something that you don't know what's going on, right? You know, you are at a loss as to, well, what's gonna, how much am I taking in here? Is this more than one serving? Some packages will tell you, some don't, right? And maybe there's where do we have a Food and Drug Administration in Guyana, FDA, like how they have it outside? I think we should have somebody here that monitors these things. I mean, at least if they don't do any work, but at least there is a body, right? Nobody checks nothing. Like I was telling you all about vinegar the other day. Was it this class I was telling about mixing vinegar? I don't think so. Was probably another class. Nobody checks to see whether the people are giving you the right concentration and all of that. All right, yeah. So let's move on. Yeah. So we talked there about um the what work is, a little bit about we can calculate work done, right? And we said that energy is the ability to do work. So to do work, we need energy then, right? And there's that connection. There's that connection between work, energy and work. And work. That connection is there, right? So let's talk a little about energy now. Good. Now, energy, they have various forms of energy. Forms of energy. Right? Forms of energy. And for this course, we're going to only well, I think not the course does cover some other type of energy a little later on, right? But for this, so far, we're dealing with what we call mechanical energy. Mechanical energy. Right? And when we speak of mechanical energy, this has to do with, moving objects around, moving things. Right? So when you speak of mechanical energy, we are more concentrated on that part of physics that got to do with mechanics. And you're going to see these terms here. You're going to hear about kinetic energy. Kinetic energy. And this is energy that a body has by virtue of its movement. So if a body is moving faster, it has more kinetic energy. If it's moving slow, it has less kinetic energy, right? So that's when we talk about kinetic energy, we talk about the energy a body has because of the speed it's moving at. And then you're going to hear of potential energy. Potential energy. And this one is a little tricky too, because potential energy is a term that is very broad. So what we're going to talk about is something called gravitation, potential energy. Right? Gravitation, potential energy. So once you hear, they put on an AL at the end, right? Instead of saying, they say gravitational. gravitation. That's why you notice, I went here, gravitational potential energy. Sometimes extra bit ties the tongue up. Gravitational potential energy, right? And why are we qualifying the term with this word in front of it? Why? The reason why is that technically, chemical energy, right? Well, let me clarify the word potential. Potential means stored energy. And chemical energy, as in, energy that is in gasoline, diesel, this sort of thing, coal, all of these store potential energy, they store energy in the form of chemical energy. So we don't want to confuse that with what we're talking about in this topic. So this topic, we are talking about gravitational potential energy. What we mean by this? Gravitational potential energy. Let me write back the term. Gravitational potential energy, right? There's an R somewhere, right? Writing with this pen, my handwriting has always been very bad. Yeah. When we speak of gravitational potential energy, what we mean, we are referring to energy that a body has by virtue of its position above the earth, right? So we have the earth, we have the ground here, the earth, and let's say a body is higher up here. You have a ball in the air there. It has a certain amount of energy compared to when it's here, right? So let's say it's here and it's here. So because this position is higher up from the ground, it's higher above the ground, this ball has more gravitational potential energy than the one on the ground. And that difference is measured by a formula, right? It's referred to gravitational potential energy. Sometimes we use this term, potential energy equal to mgh. But we know what is m, that's the mass. G is acceleration due to gravity, and h is how far above the ground the ball is, right? Now, to qualify this a little more, sometimes we don't say we say that the change, we use a delta potent PE equal to mg delta H, right? And let me tell you why we say that. The gravitational potential energy, right, is really a measure of how much energy something has, right, by virtue of how far it is from the center of the earth. Now, we can't go about saying how much potential energy anything has from the center of the earth. It's not a practical quantity that we need. What we need is, all right, how do we get a ball from the ground to maybe here? And if a ball falls from here to here, how much energy it releases, or how much energy is going to be converted to other forms of energy. That's what we're interested in. So what we basically are interested in is the change of potential energy. And that change is measured by mg delta H. And we don't use the center of the earth as the reference. Maybe we'll use, and we can choose the reference, right? We can choose, in most cases, we'll choose the surface of the earth, right? We'll choose the surface of the earth. So keep that in mind. So going back, let me go back. Let me go back to kinetic energy, right? Kinetic energy, we said, is the energy that a body has by virtue of its movement, or its speed. And there's a formula actually, right? Kinetic energy is equal to half mv squared, where m is the mass of the object and v is the velocity. Right? So the kinetic energy of a body is equal to half mv squared. Right? When it comes to the potential energy, sometimes you see this formula, right? The potential energy of a body is equal to mgh. What does it really mean? If the body is at a certain height above the surface of the ground, right? The amount of potential energy it has with respect to the ground level is mgh. And as I said, if you were to move something from one location here, maybe, all right, from here to here, the change in potential energy is given by mg delta h. Right? And if we were to go back to that work energy connection, right? Energy connection. If we want to move something from here to there, we got to do work, right? We have to do work on it to move it from there to there. We need energy, right? We need to, well, because this thing has to, for it to move from here to here, we have to do work on it, and that gives it greater potential energy, right? If we want something to move, something is stationary. Something is stationary, you know, all right? Something is stationary. And you want it to move now at a certain velocity. Let's say this thing has a mass of m. Well, we have to give it what we call kinetic energy, right? We have to give it that energy by maybe giving it a push, right? Give it a push. You need to, or sometimes we have to give it a constant force to give it a certain velocity, right? Again, because you have to exert a force, it means you have to do work, right? You have to do work. Think you're getting it? Now that we are introduced to mechanical energy, energy. We talked about kinetic energy. We talk about potential energy, right? And we talk about that work, energy connection, you know, work, energy, energy connection, right? There is a principle in physics. Long ago, they used to say it's a law, but now they realize that it's not 100% true, right? I don't want to get into the work of Einstein and all of that. I'll get into it a bit just now, right? There is a principle called the conservation of energy, right? What am I writing? I'm hurrying to spell the word out. Yeah. Once they used to say the law. Now you see in some textbook they use the word principle, right? And this is more applicable. The reason why is that I'll tell you why they had to get rid of this word law just now. But generally, what it's saying is that energy, right? The total mechanical energy of a body, basically remains constant in that energy cannot be created or destroyed. It just changes from one form to another, right? So let me explain why. All right, you have an object. All right, it's on this height. So it has a certain potential energy, right? So all right, it has a certain mass. So its potential energy up here is mgh, right? If this ball is to, for some reason, somebody touches it or breeze blows it and it slips off here, what happens to it? It starts to move down. It has a velocity now, right? It falls with a certain velocity, right? And that velocity is actually going to increase because of gravity. And it can be measured at various intervals with, all right, let me use KE. KE equal half mv squared, right? So if it falls and it hits the ground with V, the energy it has when it hits the ground is half mv squared, whatever V is, right? Half mv squared hits the ground. Usually, when a ball falls to the ground, a couple of things can happen. It can bounce, right? But you notice very often sometimes the ball don't bounce back to this height here, right? So all this potential energy becomes kinetic energy. But when the ball hits here now, it bounces back. So it does have some potential, some kinetic energy. It goes up to a certain height. It goes up, okay, comes down, and then it bounces up back. Now, why doesn't it bounce up to the top here? Sometimes it does, sometimes it doesn't. Most of the time it doesn't. Why? Anybody can say?
Is it because of force, sir?
Because of what?
The force?
Because
Or
of
the
what?
gravitational pull? Sir, the force or the gravitational pull?
It's something
Just
to
a
do
guess.
with loss of energy. What has happened if you
Okay.
realize when a ball hits the ground, you hear sound, isn't that so? You hear sound. So some of the energy, all of it is not converted to kinetic energy. Some is converted to sound. You hear, that's why when you bounce a basketball, it can be very irritating because it produces sound. So some of the energy is lost or it's converted to sound, right? As well as if you were to, anything ever fall on your foot? A heavy object ever fall on your foot?
Mm-hmm.
Does it feel warm?
I know my foot feels numb or felt numb.
Okay. There is a rise in temperature because, all right now as you're sitting listening to me, right? If you have an object nearby, you take it and kind of throw it in your other hand a little with some force. And tell me if you don't feel a warmth. If you don't feel a warmth on the hand that you threw it into. It does feel a little warmer. So there's some loss of energy or there's a transfer of energy to heat, right? To heat. The technical term is internal energy. It raises the internal energy of your hand. That's why it gets warm, right? So that's why it very often doesn't bounce back to the height it has fallen from, right? Of course, if you were to project the ball, maybe exert a force on it, so it didn't just slip off from this thing. If you were to exert a force on it and it falls with, you kind of, besides the weight mg of this ball, you exerted an additional force. The ball can hit the ground and bounce back higher. Have you ever done that with a ball? You just don't drop the ball. You can do this at home. Make this a point, right? When you have a ball another day, drop it. Very often the ball does not bounce back to the height of your hand. But if you were to exert some force, so besides the weight of the ball, you exert some force and have it bounce. And what happens? It sometimes bounces above your head, right? That's why it will go up. But ordinarily, if the ball was to just drop down from this height, it might hit the ground and then go back up, but not back to the height it was. Why? Because you have that change of energy where some of the energy becomes sound, some becomes what we call, all right, let me use the word heat, right? Wherever it hit the ground, it made it a little warmer. Sometimes you don't detect it, but it does, right? And that's what conservation of energy is. Because you say, man, if this ball had mgh up here, it converts to this half mv square. And then when the ball bounces back, it doesn't go back to the height because there was supposed to be that constant change, right? From potential energy to kinetic energy to potential energy, but it's not happening. It's not happening. Why? Because some of the energy is lost as sound. It's lost as heat, right? But the conservation of energy is saying that, you know what? It's going to change from one to the other, right? Energy is going to change from one to the other. Right? Keep that in mind. The notes got something on the principle of conservation of mechanical energy. And I just want to mention, oh, they want to go home now? All right. Y'all give me 1 second. Oh my grandchildren ain't gonna tell me goodbye. Yeah. So there's that constant interchange, right? And I mean, we humans have harnessed this to our advantage, right? Um, well, let's talk about mechanical energy in particular, right? Um, I think one time in Guyana, that was our dream, and we can't seem to realize that dream in Guyana. You want to take, let's say you have a waterfall, and water is falling down here. Well, when the water is up here, right? Let's say you have one, let me just say 1 ton water. 1 ton water, 1 ton, right? Which is 1,000 kg. That water, and let's say this thing is, okay, let's go with 1,000. That's too much, right? 1,000 meters. What's the height of Kaieteur? Anybody remember? How high is Kaieteur? I think I'm too ambitious here. Let's say we have a waterfall of 100 meters. Let me not be too ambitious. 100 meters, right? So the energy of this water here, right? By virtue of where it is, I'm not saying water got far more energy than that, right? But let's just say by virtue of where it is on the Earth's surface. So this is the ground. So the potential energy of this this water is mgh, right? 1,000 by 10, which is g, times h, which is 100. That's how much? That's 1 million joules of energy, right? 1 million. When that water comes down, falls down here and hits the ground here, right? All of that energy is going to be converted kinetic energy. Well, you know, sometimes the water don't bounce back. The water just rumbles and go along, right? So it will have some speed going in a different direction. But then down here, it'll be pretty warm. And then it's very thunderous, right? You hear the rumble of the waterfall. Anybody went to Kaieteur? Tell us your experience. Do you hear the sound?
You do,
Anybody?
sir. You do hear the song.
You don't hear the sound?
Hello.
Yes, you do. You do hear the song, sir.
Is it very loud?
Very loud. And
Okay. I'm
thunderous
such an old
almost.
person and I have not been to Kaieteur. So teach me. Yeah, so you're saying
You-
it's very loud, right? So here, what's
Very
happening
loud.
is the potential energy of this water is becoming now, as we said, The water is going to flow, it's going to bounce up back and all of that. So it's going to change to kinetic energy. It's going to change to sound. That's what you were hearing, the thunderous sound of a waterfall. And then down here is going to be pretty warm because that water is hitting rocks. It's hitting water and rocks. So it's going to be very warm there, right? If you catch water from there, you don't need a hot water system at home. Pretty warm. So what we're trying to do now, we're trying to harness this. As it comes down here with that speed, we put a turbine here. So we put a turbine here. So when the water flows in here, it turns the turbine, and the turbine will now turn generators, and we get electricity. Right? That's what we're trying to do. I don't know what has happened to Amalia Falls. They see the little gas now, so they forget about Amalia Falls. Billions of dollars have already been spent, and I don't know what they're doing with the project, but that's our dream. If I remember well, from a small boy, I remember when Burnham used to rule this country. He really wanted to harness one of those falls, right? There was a fall in the Potaro River. Trying to remember what's the name of the fall, and he wanted to harness it. But of course, we hadn't the kind of money and resources like now. I think we have the money now, we can do it, but I don't know what's happening. But that's our dream in this country, to harness, the power of our waterfalls, right? I have seen, I know in Lethem they had the Moka Falls. Was that it? Did I get it right? Or the Kanuku? What was it? I forgot the name. And they actually had a system there to harness that water. I was seeing this guy was visiting somewhere in the interior. There was another small system that they were using to generate electricity as well. So yes, they have these smaller systems that they can use, to turn this potential energy into electrical energy, And I wish we are there someday, right? On the coast here, you see a lot of people with windmills, right? They're using the energy in the wind to change it to electrical energy, because that's the energy in demand, right? We want electrical energy, right? Look what has happened. I just want to show you something. This morning I was watching my modem and the telephone system. GT&T made the thing in such a way that your telephone is connected somehow to the internet. So for your telephone to work, you have to have your internet, your modem on. So you have to burn energy night and day, 24 hours for telephone to work. How you like that? When you had that line phone where just had a cable coming, they used to gotta run something to keep that phone line alive, right? But now they put the burden on you, the customer. You all notice that? So if you want your phone to work, like I have fiber, right? For my phone to work, I have to have my modem on. To have the modem on, I have to have electricity. Right? So you see what's happening? We're creating more demand. And now all of you want to use the internet, AI. For that to happen, they have to use they have to use a lot of energy to keep what we call data centers running. Lots and lots of energy is needed for those things, right? So AI isn't coming at zero cost. It's costing people and it's costing the earth quite a bit of energy to run those centers. I remember the other day, some residents in America, they were complaining. They had these reporters looking at this man, Elon Musk, set up a data center near to their town. And they said this used to be a very quiet town. And Elon Musk bought over, it was an old mill. He bought over the building and he installed inside these, what we would call data servers, you call it, right? And those things, they use enormous amount of energy. So they have generators running 24 hours. And the people in the tongue now, they're hearing a humming the entire day and the entire night. The thing hums just day and night. The people say, they have to now insulate their house from the sound and so. Yeah, so energy is a big, big, big problem around the world now. And harnessing it is such a big study right now. Solar, wind, hydroelectric. And now we gone and we want to use the gas that is coming out of the oil wells to generate electricity, Good. So we talked there about quite a bit of stuff on energy, right? We want to close off our session. I think I talk a lot, and we want to talk a little about power, right? And what is power, right? And the notes I sent you again described or defines power. Power equals work done over time, right? Or time taken, right? Sometimes you see energy transferred instead of work done. Because remember, I keep telling you that energy is the ability to do work. So the two can be used kind of interchangeably. So work done over time taken, right? And power, while work done is in joules and time might be in seconds, again, they don't use that unit, right? The unit they use is the watts. Right? So it's funny. The man who instead of this they use the watts, right? W, watts. The man who did a lot of work again in the area of work energy is also named James. Funny, am I getting this right? James Watt. I spoke about James Joule. I hope I'm getting these names right. You almost second check me out, do some research. James Watt. So they borrow his name and say, man, let's, as a tribute to him, we're going to name the unit of power the watt, right? And basically, 1 watt is if 1 joule is expended in 1 second, right? If 1 joule is expended in 1 second, it's 1 watt, right? So like, okay, let's say, all right, you have to lift something. So you have you're at work, and this is some content. You have to lift an object. You have to lift an object that is 1 kilogram. And let's say this thing is 1 meter high, right? 1 meter. And you do that in, let's say 2 seconds. Can you lift something? Yeah, maybe you can lift that, right? So you have to lift 1 kilogram. So the force, the weight of this thing is 1 times 10 newtons, right? So it's 10 newtons. You all know how we get that, right? Weight is equals to mg, right? And the energy, remember you have to give it potential energy there, right? Or the work done. Let me use it this way. Work done equal 10 newtons multiplied by 1 meter, which is 10 joules. And if you do that in 2 seconds, the power exerted is 10 joules over 2 seconds, which is 5 watts, right? 5 watts. And that's how you measure power. Of course, things like electrical power, and so we're going to touch on that a little later on. We're going to deal with that a little later on, right? For example, let me just give you a quick example. So let's say you're pumping water at home, and this tank got about what? My tank up here, let's say you have 1 meter cube of water, right? 1 meter cube. So 1 meter cube of water will be 1,000 kilograms, right? From the density of water. Let's say the density is one. Sorry. The density of water is 1,000 kilograms per meter cube, right? So you have all this water in here. And you have to pump all this water up to a tank. Maybe the tank is, what's the height of your house? Let's go about 5 meters, 15 feet. So the tank on top here, your trestle, and you have to pump it up to a tank there. And the tank is from the ground here is 5 meters, right? You have to lift 1,000 kilograms, 5 meters up, right? And let's say you have a pump. You have a pump that I think a typical pump, let's say it's 1,000 watts, right? Or it's 1 kilowatt. That's what they will say. And you want to know how long will that take? How long will that take? Right? Well, let's go with how much energy is needed to take this from here to here. So the work done would be equal to the mass by G by H, right? 1,000 by 10 by 15. How much is that? Somebody help me with the arithmetic here.
150,000
150,000 joules.
joules.
Good. So that's the amount of energy you need to move 1,000 kilograms of water 5 meters up. Oh, sorry. Did we say 5? I put 15. It should be 5, right?
Yeah.
So what's this? I need to take out the 1 in front?
50,000, sir.
So I'll take out the
50,000
1.
joules.
Good. So you need 50,000 joules, right? Of energy to take it up. But your pump is giving you 1,000 watts, which means, what that means? That means the pump delivers 1,000 joules every second. That's what the pump is doing. The pump delivers 1,000 joules every second. That's what 1,000, if a pump is 1,000 watts, it's delivering 1,000 joules every second. So how long will it take to pump that water? It will take, what is a powerful pump? It's going to deliver 50,000 joules in 50 seconds, in less than a minute. All right, this is a little water. This is not plenty. In less than a minute, that pump will pump up that 1 meter cube of water 5 meters high. Right? But if you have a bigger tank and you have to move more water, well, you know how to do the calculation. Right? So you see how we can convert this electrical power that the pump has, and we can say, well, how long it will take to do a particular amount of work. Right? Well, we'll get to this when we do electricity and so some more. There's a final relationship I want to share with you when it comes to power, right? And that relationship got to do with it has to do with like the movement of a vehicle, right? Power is also defined by FV, where F is attractive force, and this V is the velocity, right? So this applies to like a car. You know, you have a car and the engine is what pulls it along, right? So if you want to travel, right, at let's say you want to travel at a speed of let's just use a number, and I'm going to go with this unit, even though your car would be in km per hour, right? I'm going to use meter per second just for the simplicity. So you want to travel at 30 meters per second. Please remember how to convert, right? And the resistive forces on the wheels because of the weight of the car and whatever load it's carrying and so on. The resistive force is, let's say, 1,000 Newton. Now, this car will have to actually, or the engine will have to be working at this power, 1,000 multiplied by 30, which is 30,000 watts, right? In other words, every second, this engine has to produce 30,000 joules of energy to drive this car. Right? So this is mostly, it has to do with something that is moving. If you want to pull an object along, right, at a certain speed, whatever force, and it doesn't have to be a car. If you want to pull an object along, right, and you want to give it a speed of, let's say, 1 meter per second, right, and this object is, let's say the weight is, let's say it's a box, you know, you want to pull it on the ground, raw force, you know, and you want to give it 1 meter per second, which you wouldn't do, right? Most of us, we would use some kind of machine, something with a wheel, right? But I'm just saying, if you want to just drag this box along at 1 meter per second, and the box is, let's say, 100 newtons, right? Which is about 10 kilograms yeah, 10 by 10, 100, yeah. It's 100 Newton in weight. So the force the power you would have to exert is 100 by 1, which is 100 watts. In other words, every second you would have to exert 100 joules. You would have to spend 100 joules every second to pull that box along at 1 meter per second. But as I said, this relationship often is used in connection with, you know, the power of a vehicle is producing, the engine is producing, right? It's not used so much with, you know, humans pulling objects along and all of that. Good. So what we'll do, I think we'll stop there. I think I spoke quite a bit, and I don't want to overburden you, you know. So we'll stop here.